Okay, today we will solve 5 simplest problems from AIME 1994, and it can be considered as advanced AMC preparation. You will figure out pretty quickly that the easiest problems from AIME, they are very similar to the most advanced problems from AMC. But here you have these problems at the beginning of the paper, and in AMC you have such most advanced problems at the end of the paper. But if you solve enough of these, in this case you will perform very well at AMC, and you will greatly improve your math level as well. So let's start from the first one. The increasing sequence 3, 15, 24, 48 consists of those positive multiples of 3 that are 1 less than a perfect square. What is the remainder when 1994th term of the sequence is divided by 1000? Let's look at this one. So we have a sequence, but before we start solving, it would be great for us to understand how the sequence is organized and what is the structure of the sequence. As you can see here, we have two requirements. The first one, each number is a multiple of 3. Each number is divisible by 3. I will remind you that you can very quickly check if the number is divisible by 3 just by adding the digits of this number. For example, for 48, you add 4 plus 8, 12, divisible by 3, then 48 is divisible by 3. If the sum of digits is not divisible by 3, then the number is not divisible by 3. So multiples of 3, but in addition, each number here is 1 less than a perfect square. And let's just understand how this sequence is organized. And let's check. For example, for 3, you have that it is 4 minus 1, and it is really 2 square minus 1. So 1 less than a perfect square. Well, for 15, it is 4 square minus 1, and it is really 1 less than a perfect square, and it's divisible by 3. So, for example, for 24, it is 5 square minus 1, and for 48, it is 7 square minus 1. Well, now it's not clear what is the structure of our sequence. At this moment, it's very difficult to tell. In this case, if we don't know exactly what is, let's just continue a little bit further. For example, it would be reasonable to assume that the next one would be 8 square minus 1. Let's check if it works for us. It is 63, and it's really a multiple of 3, so it is the next term of our sequence. That should be here. Let's check another one, 9 square minus 1, and it is 80, so it's 1 less than a perfect square, but it is not divisible by 3. Doesn't work for us. Let's go a little bit further. So, for example, 10 square minus 1, and it works perfectly for us, 99. 11 square minus 1, 11 square minus 1 is 120, works for us. But if you go to 12 square minus 1, you will get 143, which doesn't work for us. So, what is a pattern here? Now we see that 12 square minus 1 is not a part of our sequence, 9 square minus 1 is not a part of our sequence, and maybe we also skipped some options here. Let's look. For example, here we have 2 square minus 1, and here we immediately have 4 square minus 1. It means that probably if we look at 3 square minus 1, it is 8, and it is not a part of our sequence again. So 4, now we jump to 5, and from 5 we immediately jump to 7. And it means that probably 6 square minus 1 was skipped, and indeed it is a 35, and it is not a part of our sequence because 35 is not divisible by 3. Now, if you pay a little bit attention and look at the pattern what we have to discard numbers like this: 3 square minus 1, 6 square minus 1, 9 square minus 1, 12 square minus 1. Well, you can immediately notice that if you have a multiple of 3 squared, minus 1, then it doesn't work for you. It is not a part of your sequence. However, it looks like any other number that is not a multiple of 3. If you square this number and subtract 1, you will get something that is divisible by 3. And at first it looks like we really have way too many numbers here, because number is not only 1 less than a perfect square, but also it's like a multiple of 3. It looks initially a little bit even suspicious that we have so many numbers that not only 1 less than a perfect square, but also divisible by 3. But it's very easy to explain. Really, it comes from the fact that any number a can be divided by 3 with a remainder. For example, a equals 3p plus remainder. And there are only 3 options for this remainder: 0, 1, and 2. And it's very easy to understand that if a has a remainder 1 or 2 when divided by 3, then a squared minus 1 will be really divisible by 3. Well, let's check. For example, if a equals 3p plus 1, it means that a has a remainder 1 when divided by 3, similar to, for example, 4, right? A equals 4 works in this case. In this case, a squared minus 1 equals 3p plus 1 squared minus 1, and if you simplify it, you will get 9p squared plus 6p, which is divisible by 3. It is a multiple of 3, and it means that each number like this, squared minus 1, will be a multiple of 3. So every number a like this will work for us. You can also check that every number a equals 3p plus 2, that has a remainder 2 when divided by 3, also will work for us. And of course, if you have a number a that is simply a multiple of 3, a equals 3p. In this case, a squared minus 1 equals 9p squared minus 1. Of course, it is not divisible by 3, because this part is divisible by 3 and minus 1 is not divisible by 3. This is it. So this one doesn't work. Let's just discard it. And as you can see here, the structure of our sequence now is super obvious. We take every number squared minus 1 that is not divisible by 3. It will be a part of our sequence. So if number is not divisible by 3, then the square of this number minus 1 is divisible by 3. But if number a is divisible by 3, then this number squared minus 1 is not a part of our sequence. And now we understand completely and very clearly how does the sequence look. In this case, it makes a lot of sense to rewrite our sequence in a simpler manner. So let's start with 3. For example, 3, it is 2 squared minus 1. So here, what we expect to be the next one? 3 squared minus 1, but it is a multiple of 3, and this one we have to skip. So this one have to be skipped. Let's go to the next one. The next term should be 4 squared minus 1. 4 squared minus 1, and it will perfectly work for us because 4 is not divisible by 3. So, and in this case, it works for us. We cannot even write what it's equal to. So we just know that it is a part of our sequence. 5 squared minus 1 works for us, but 6 squared minus 1, multiple of 3 here. 6 is a multiple of 3. Doesn't work for us. Let's go to the next step. 7 squared minus 1 will be a part of our sequence, but what about 8 squared minus 1? Also works, and 9 squared minus 1 will not work. Just for everything to be super simple, let me write 3 more terms. And as you understand that 10 squared minus 1 will work for us, 11 squared minus 1 will work for us, because those are numbers that are not divisible by 3, and the next one, 12 squared minus 1, will not work for us. So now everything is like super simple. And what do we need to find here? We need to find 1994th term of our sequence and to divide it by 1000 and to understand what would be the remainder. Let's just mark our sequence here. So it is a part of our sequence, this one skipped, it is a part of our sequence, this one skipped, it is a part of our sequence, this one skipped, and it is a part of our sequence. And then the pattern repeats. And as you can see, we have a very clear pattern from this moment. Let me use a rectangle to emphasize. So here you have a pattern like this. In this rectangle, you have 2 terms of the sequence, and the next number will be skipped. Here you also have 2 terms of the sequence, the next number is skipped, and here you have 2 terms of our sequence, and the next number is skipped. As soon as you see patterns like this, it makes a lot of sense to use these patterns to simplify the solution of your problem. And here, after a while, we need the term with the number 1994. 1994. Let's understand how to get this one. Well, at first, we see that each rectangle like this contains exactly 2 terms of our sequence. Well, it is not a part of our pattern, so this one is like excessive. We don't need it. And we have no problem to discard this term. We just throw away the first term from here, and we will start from here. So here, we will be left with 93 terms of the sequence, and this one, 4 square minus 1, it will be the first term of our sequence, this one will be the second term of our sequence, and we can start from here, and in this case we need here the term with the number 93. Okay, so how many rectangles will we need to go through to get to the number 93? Each rectangle contains only 2 terms of our sequence. Let's divide 93 by 2. 93 equals 2 times 996 plus 1. Well, very simple, you can check that it is the case. It means that if we go from left to right, we need to pass 996 rectangles, and when we completely cover these 996 rectangles, we will go to the next one, to the rectangle with the number 997, and exactly the first number here in the rectangle 997 will be the number that we need. And it simplifies the solution, because look, at the first rectangle, how to make some sort of connection between rectangles and numbers. Let's look at the first rectangle here. What number do we have at the end, the number that we discard? The rectangle with number 1 at the end has the number 3 times 2 squared minus 1. It's okay. So here, rectangle number 2, what number does it have at the end here? It is 3 times 3 square minus 1. It's a rectangle number 2. So you will see that this digit will change and nothing else will change. So for example, in this rectangle number 3, what number do you have here? It will be 3 times 4 square minus 1. It's in the rectangle number 3. So in the first rectangle, the ending number that is discarded here is this number, and in the second rectangle, the number that is discarded looks like this. In the third rectangle, the number that is discarded looks like this. So the first rectangle, here you have 2 for the first one. For the second one, here you have 3. For the third one, here you have 4. And of course, you can immediately say that there is a pattern. For the rectangle with number n, at the end, this number that is discarded looks like 3 times n plus 1, all of that squared, and minus 1. It is the number that is discarded here. What does it mean for us? It means that when we finish on the rectangle with number 996. So assuming that we finished on the rectangle with number 996, what would be the number that stays right next to the number we need, the number that we discarded? What would be the number at the end of the rectangle with the number 996? Well, let's substitute. Instead of n, we substitute 996, and we will get 3 times 997, all of that squared, and minus 1. And the next term here, what would it be? Well, we go on the terms like this. So we go square of the number minus 1, and then square of the next number minus 1. So if here at the end we have the square of this number minus 1, on the next position right here, we will have the square of the next number that goes right after this. So it will be 3 times 997 plus 1. It is the next number, and after that you square it, and minus 1. And this will be the number that goes right after the rectangle 1996. So it will be at the beginning of the rectangle 997. So with this number, if you look at this one, 3 times 997 plus 1 squared minus 1. Let's simplify it. When you square it, the 1 will simply cancel out, and you will get the number like this. 3 times 997 squared, plus, after that you will get 2 times 3 times 997. And it is just the explicit form of the term of your sequence, with the number 1994. So it is the term of your sequence with the number 1994, and after that you need to find the remainder when this number is divided by 1000. And here comes just a simple algebra. You just multiply these numbers, and after that the remainder when all of that is divided by 1000, you should get 0.63, or simply just 63. So the answer here, 63, is a correct remainder when this term, this number, if you calculate it and divided by 1000, the remainder will be 63, and it is the right answer for this problem. So let's move to the next one. Okay, the next one will be a very simple geometry, and if you know geometry on a very basic level, it's the great advantage for you, because you will be able for sure to get extra points at AIMC and AIME as well. The geometry here is usually very straightforward. It almost never requires some sort of complicated approaches. Usually you should just pay just basic attention to details. For example, here in this problem, I had many students who got very simple mistake. They assumed that this square for some reason is inscribed in this circle, and they assumed that the center of this square ABCD is the same as the center of this big circle. And it would be true, of course, if the square is inscribed, then the center of the square is the same as the center of the circle, but not in this case. You can pay attention here that C and D, they are both inside the circle. Not all the vertices of the square are on the circle, so the center of this square is not the same as the center of this big circle. It would be only in the case if it's inscribed. In addition, it's very important to remember that if you have two circles that are tangent, and here they are tangent internally, then you should always mark 3 points that always belong to the same line. And I'm talking about center of one circle, center of another circle, it would be somewhere here, and the point of tangency. These 3 points always belong to the same line. So when you have problems like this, it is the first thing that you should do. You should mark 2 centers of circles and points of tangency, and they always belong to the same line. Well, you can prove it just as a separate problem. It's a very simple problem on geometry. Why, if you have a tangency of 2 circles like this, obviously you have a common tangent line here, why these 3 points belong to the same line? And of course, if you have 2 circles that touch externally, for example, one circle like this, and another circle will be, let me draw another one, like this, and let's assume that they touch externally, so like this. It will be the same situation. In this case, the centers of the circles and the point of tangency always belong to the same line. So if you take this center of the circle, this point of tangency, and this center, always on the same line. The same in this case. So it's very important. It's just a basic of geometry. Again, you can prove it as a separate problem here. So let's start with what they want. So PQ is a diameter 10. So a circle with diameter PQ of length 10. So basically they tell us that this distance is 10. So let's mark it on our picture. So it is 10. Is internally tangent at P to a circle of radius 20. So this big circle has a radius 20, and we already marked the center of the big circle, so it means that we should maybe draw some radius here. Well, we should connect this point to the point at the border of the circle. So basically we need to connect maybe like this one, it is 20, or this one is also 20. And in this case, so let's mark 20. Square ABCD is constructed with A and B on the larger circle, as we see, and CD is tangent at Q. CD is tangent at Q to a smaller circle, we see it here, and the smaller circle outside ABCD. Smaller circle is outside the square. The length of AB can be written in the form m plus square root of n, where m and n integers, you need to find some of these numbers. So very straightforward. So what is the next mistake that students make in this problem? Usually students tell that this point is the center of the square for some reason, and it means that this angle, in their opinion, is 90 degrees, and they find this AB by Pythagorean theorem that it would be 20 square root of 2. Of course, it's not a correct solution. And why? Because once again, this point that we marked here, it is the center of big circle, and as we figured out, this point is not the same as the center of your square. It is not the case. Okay, let's look here at basic geometry. So what we see that here we have a center of big circle. This portion is 10. Obviously we can write that this portion here should be also 10, because it is a radius, it is 20. We need to find eventually side AB, side of your square. Well, let's introduce some variable for it. Let's make it x. So each side of the square is x. Of course, you can see that the picture has a complete symmetry with respect to this line. Complete symmetry, and it means that this portion is the half of the side of your square. So it's x over 2. X over 2. And the main thing here that you need immediately notice that here you have a trapezium, and these angles are 90 degrees, and you can even separate it for your own for convenience. So let's draw this trapezium here, so we need only this one. So let's draw this one. It will be 10, and the other one on the other side will be x. This one is perpendicular to the basis, and this one will be 20. So we have a trapezium that looks like this. So let me make 20 here. So this one is 10. I just like draw it upside down, but the structure stays exactly the same. So, and this one is x over 2, and this one is x. So we have a picture like this. And from here, it's very obvious what should we do next. If you solved simple problems on geometry, where you need to find some side of the trapezium, you always do one thing. You always make an altitude like this of trapezium, and you separate a rectangle, and after that, when you separate it, you use Pythagorean theorem for the remaining triangle. It's like the standard way to solve these problems with a trapezium. So here, as soon as this one is a rectangle, this is 10, and this one is x minus 10, this is x minus 10, and this is the same as this one, x over 2, and now you simply apply Pythagorean theorem to this small rectangle. So let's go a little bit like on the distance from the picture, so we'll have like a normal image. So we have this triangle, and this side is x over 2, this side is x minus 10, and this side is 20. We apply Pythagorean theorem here. The square of hypotenuse, which is 400, equals the square of this leg, x squared over 4, plus the square of this leg, x minus 10 squared. Well, let's solve this equation and we will find x, and it will be the end of the story, because x is the side of our square, and that's what we need to find. So let's just not mess up the numbers. So we will work with this one. X squared minus 20x plus 100 plus x squared over 4, it's on the right side, and on the left side we will have 400. So let's bring 100 on the left side, so 300 equals, here x squared plus x squared over 4, we have 5x squared over 4 minus 20x, and what should we do here? Well, the only thing that we should do here, probably we should divide everything by 5. It will probably simplify our equation. You see, every number here is divisible by 5, and we will get rid of big numbers if we do it. For example, it will be 60 equals x squared over 4 minus 4x, and now we just multiply everything by 4 to get rid of 4 on the bottom. So it will be 240 equals x squared minus 16x. And from this moment, we simply solve a quadratic equation x squared minus 16x minus 240 equals 0. So, and in this case, we will go in a very straightforward manner. We calculate discriminant, which is equal b squared minus 4ac. So b squared is 256, and minus 4ac, 4 times this one with minus, it will be plus 4 times 240, which is 960. And this number, if you add up, you will get 900 plus 256, 900 plus 256, you will get 1156, and after that you also need to add 60 here, and it will be 1216. Yeah, okay, so it is your discriminant, and eventually x equals minus b, so it will be 16 plus minus square root of discriminant 1 to 16 divided by 2. Obviously, you have two different solutions here, but it's like quadratic equation, and if you have here minus, the total result will be negative, so minus is discarded. Eventually, the only one that works for you, because x is positive, is 16 plus square root 1216 divided by 2. Well, and this number here, beneath the square root, it's obviously divisible by 4. You can check it by the last two digits. If the number formed by the last two digits is divisible by 4, then this whole number is divisible by 4. So if you divide 1216 by 4, it will be equal, obviously, 4 times 304. 4 times 304, and it should be equal 16 plus 2 square root 304 divided by 2. And here you have 8 plus square root of 304. So at this moment, you should stop right away. You shouldn't try to take any other numbers from this square root. Well, of course, 304 is also divisible by 4, right? Because 300 is divisible by 4 and 4, but you don't need to bring any other numbers from the square root here. Why? Because they want you to get your answer in the form. The side of the square should be in the form m plus square root of n. Just pay attention that there is no other numbers here in front of square root. There is nothing here. It means that as soon as the side of your square looks like this, you are good to go. So it means that we already have a proper answer. And it looks like this. This is m, this is n, and you need simply to find the sum of these numbers. Find m plus n. So in this case, m plus n equals 312. And it is the correct answer for this problem. Okay, so this one was very simple. Let's go to the next one. Okay, let's solve very simple functional equation number 3. And if you want to be able to solve an equations like this, where you have functions, it's called functional equation. In this case, it makes a lot of sense to start from AIME or British Math Olympiad, like BMO. Both these competitions, they have a lot of these problems, and it is very reasonable level of difficulty. So they are not very simple, but in the same time, all of that is very solvable. And if you want to be able to build your confidence and to practice in such equations, AIME and BMO is a great source. I had students who always wanted to solve problems like from International Math Olympiad. IMO also have a lot of functional equations, but the difference is that on IMO, these problems, they may look very simple, they may look very short, but the level of difficulty sometimes is just insane, and sometimes it even takes you 1 hour just to explain the solution, and of course it takes more time to solve. So it will, if you start from IMO problems, it will be just way too much. You will probably end up nowhere. But if you start from this, you will be able to build your confidence and really to improve the current level, especially if you are new to such problems. So we have a function f with a property that for each number x, f of x plus f of x minus 1 equals x squared, and f of 19 equals 94. What is the remainder when f of 94 is divided by 1000? So immediately we need to understand that basically they want us to find f of 94. And how most of people try to solve this problem, they know f of 19. Well, they immediately try to substitute here 19 instead of x. So let's try to do it. F of 19 plus f of 18 equals 19 squared. Well, what we know here? Here we know 19 squared, and we know f of 19, which is 94. And from here we can find immediately f of 18. once we know f of 18, we substitute 18 here instead of x, and we will get an equation that looks like f of 18 plus f of 17 equals 18 squared. And again, here we know this number, and from here we can find f of 17. And so on. You can continue, and you will be able to find f of 16, f of 15, and so on. And everything looks great. However, it is not the right direction. So you go from 19 to 18 to 17 to 16 to 15, and you can find all these values. However, you need another one. You need to find f of 94. So this approach initially looks very reasonable, and it's very simple. But it's not the right way to go. You need to find f of 94. So let's start with this number. F of 94, well, let's substitute here 94 instead of x, plus f of 93 equals 94 squared. Of course, I need to find this value. That's what I want to find. And it makes a lot of sense to express f of 94 equals 94 squared minus f of 93. And here I immediately see that this one is a well-known number. However, if I know this one, I will immediately be able to find f of 94. So it makes a lot of sense to focus on this one. What is f of 93? Let's substitute here 93 instead of x. We'll get an equation f of 93 plus f of 92 equals 93 squared. And again, by using the same trick, we express f of 93 equals 93 squared minus f of 92. And you can see that these equations look similar, and what you can do, you can take f of 93 from here as this expression and substitute it right here. You will get f of 94 equals 94 squared minus, and here you shouldn't forget parentheses just not to mess up the signs, 93 squared minus f of 92. And here you will have difference of squares, which is also a great sign that you are probably on the right track, because difference of squares like this can be calculated very fast. It's like the first number minus second number, and the difference is just 1, and it simply times the sum of this number. So it will be f of 94 equals 94 squared minus 93 squared. We will leave it like this at the moment, plus f of 92. And obviously, it worked for us one time when we expressed f of 93 by using this formula. Well, it will work for us again. Let's work with f of 92 plus f of 91. It is equal to 92 squared. From here, we can express f of 92 equals 92 squared minus f of 91. And of course, it makes a lot of sense for us just to take this expression and substitute it here instead of f of 92. We will get f of 94 equals 94 squared minus 93 squared plus 92 squared minus f of 91. And you obviously understand now where it will go, because when we express f of 91, what would it be? It would be 91 squared minus f of 90. So it will be like this. And here you will get again difference of 2 squares. This is it, as simple as that. And f of 90 will be with plus, because this is in parentheses, and when you expand, this one will be the plus. So let's write the formula that we have now. F of 94 equals 94 squared minus 93 squared. The next difference of squares is 92 squared minus 91 squared, and plus f of 90. And obviously you understand very well how it will go further. So we will have differences of squares here again and again. The only thing that we need to understand when we need to finish. And we need to finish at the moment when this one is already well known. You see, f of 19. So here somewhere, f of 19 equals 94, right? F of 19. So we need to understand where should we stop. So we start with the 94 squared, 93 squared with minus, 92, 91, and this one will be even, this one will be odd. So this one will be even, and this one will be odd, right? odd. So, and let's go close to 19. So here we have f of 94. Let me just waste a little bit, like several seconds, and to write this formula once again, just for everything to be super clear. So this difference, 92 minus 91 squared, and eventually plus and so on. When we approach 19 from the left side, we approach it from the left, what will we have here? We will have difference here like even minus odd. Let's go close. So 22 squared minus 21 squared will be a part of our story. Okay, then the next one will be 20 squared minus f of 19. And here, if you substitute f of 19 like 19 squared minus f of 18, you will continue further and you will get this difference of square, 20 square minus 90 square here, but you don't need to do it. So you can stop here right away, and it will be the end of your story. So, and all these differences that you have here, it's very easy to calculate. Once again, the formula here is 94 minus 93 times 94 plus 93. So let's get here the difference, and it will be 94 plus 93, it will be 187, and here you will see that the same, the difference is 1, but we're interested at the sum, right? So what is the sum here? This number is 2 less than this number, and this number is 2 less than this number. So the sum of these will be 4 less than this number, and we will get 183. So the difference will be 4 between them. The next difference also will be 4, so it will be 179, and so on. And let's calculate this one, this number that here at the end, you will get 22 plus 21. It will be 43 here. And obviously you understand that here you have an arithmetic sequence. So it is arithmetic sequence. You start from 43, and then you add up plus 4, plus 4, plus 4, plus 4, and you end up here. And the final number here that we have, we can calculate it manually. It will be like 400 minus f of 19, which is simply 94. So this part is not a part of our arithmetic sequence. And here comes very simple algebra. So this difference is obviously 306. So this one is 306. And let's work with this sum. Just remember, when you work with arithmetic sequences, it's very important to use some super simple formula that will never give you any trouble. So when you work with arithmetic sequence, the best formula is the first term plus the last term divided by 2 and times how many terms you have in your sequence. It is the best formula. When you have a sequence, so you add the first term plus last term divided by 2 and multiply how many terms do you have in your arithmetic sequence. And it is also equal to the sum of the sequence. Let's start with this one. 43 is the first one, 187 is the last one. Well, the sum of these numbers is 43 plus 187 divided by 2. So times how many? Let's understand how many terms do we have here. We know that each jump we goes just by 4. Each jump by 4 gives us the next term. So let's solve an equation. 43 plus several jumps by 4 plus 4 times k. K is the number of jumps, and we end up at 187. Well, if we solve it, we will get 4k equals 187 minus 43. It will be 144, and k equals 144 divided by 4. It will be 36. 36, if you multiply it, you will get 134. Okay, so 36 jumps need to be done from this point to end up here. So one jump, second jump, third jump, and so on and so on. And after 36 jumps, we will end up here. each jump here gives us the new number. Each jump gives us the new number here, but also there is an additional number, this one, that is not connected with any of these jumps. So it means that 36 jumps, 36 numbers are here, plus this number here. So it means 37 numbers. And it is the total sum of our arithmetic sequence. And also don't forget to add 306. So this sum, 187 plus 43, is 230, and 230 you divide it by 2 and you get 115. 115 times 37 plus 306. And after that, if you solve this one, you just calculate this number, and you need to find the remainder when this number is divided by 1000. And if you calculate it correctly, the remainder when all of that is divided by 1000 is simply 561. And it is a correct answer for this problem. So we're left for today with a couple of problems related to sums. Problem number 4 is the first one, and in my experience, students usually don't like to solve these sum-related problems. But what I can tell you that in AIME or similar math competitions like Math Prize for Girls, these problems related to sums, they are usually very simple. You should just pay attention and to understand what is the structure of the sum. In many cases, it will be some sort of periodic structure. For example, you will have 4 terms, and the next 4 terms will be first 4 terms multiplied by some number, for example, by 1 over 2. And the next 4 terms will be previous 4 terms again multiplied by 1 over 2, so you will have sort of geometric sequence. And in some cases, the sum will look in a very simple way. For example, you will have repeated patterns. For example, you will have 0, 0, 0, 1, 1, 1, 2, 2, 2. So in every case, you should really investigate how this sum really looks to understand its structure, and it will be the key to solve the problem. And in our case, the problem looks like this. Find the positive integer n for which this sum equals 1994. Let me remind you simple notions that you probably already know. So what is the floor of x? Well, very simple. It is the closest integer on the left of x. So if you mark x on numerical line, it is some number, not necessarily integer, but you can always approach x from the left and find the closest integer on the left of x, so a. So in this interval, there are no other integers because a is the closest from the left. And in this case, this one, a is simply floor of x. Or we can say like here that a is the greatest integer less or equal than x. It is the first one. What is log? Log base a, b. It is simply a power. The power to which a should be raised to get b. Once again, it is a power to which a should be raised to get b. So if it's n, then it is a power. It means that a to the power of n should be equal to b. Or n is a power, log a b equals b. So very simple notion, and you should look always at logarithm as to the power. In this case, it's very easy to understand what would be the value, for example, here. Log 2, 1. 2 should be raised to some power to get 1. It's obviously 0. What is log 2, 2? So 2 should be raised to some power to get 2. It is obviously 1. What is log 2, 3? 2 should be raised to some power to get 3. And what this power is, if we try to make it 1, it's not enough. 2 to the power of 1 is not enough. So this power is more than 1, because 2 to the power of 1 is less than 3. But if we try to make it 2, 2 to the power of 2 is already 4. It's more than 3. So this power to which 2 should be raised to get 3 is between 1 and 2. We can make it just simple. It's something about 1.5. But the most important thing for us, that it's in the interval from 1 to 2. And we are considering next the floor of this number. But what is the floor of the number that is on the interval from 1 to 2? Well, it's obviously 1. So this is 1, this is 1, this is 0. And let's continue a little bit to understand the structure of this sum. So the next one will be log 2, 4. And it's obviously 2, because 2 to the power of 2 is 4. And the next one will be 2. Let's continue a little bit. Log 2, 5, and we will already need this floor here. So 2 to some power is 5. So this is a power to which 2 should be raised to get 5. Well, it's obviously more than 2, but already 2 to the power of 3 is already 8. So this power, this number, is between 2 and 3. So it's in the interval from 2 to 3, this number from this interval. And what is the floor of this number? Well, obviously it's 2. So it will be 2, or by the same reasoning, you can get that log 2 6 floor of it equals similarly 2, and you will have 2, 2, 2 several times. And when this pattern with 2 will finish, it's very easy to understand. It will finish exactly at the moment when you come to the point log 2, and here you will have 8, because in this case it is precisely 3, and it will be equal to 3. And before that moment, log 2 7 floor, it will be also 2. So next you will have 3, and you can easily understand that after that you will have 3 3 3 3 several times. After that you will have 4 4 4 4 several times, and so on. So now we understood how our sum looks in general, that it has at first 0, then 1 1, then 2 2 2, then 3 3 3, 4 4 4, and so on. So our sum has a pretty simple structure. The only thing for us, it's not yet clear how many numbers of 3 we have here, how many numbers of 4 we have here. So we need to understand in a more precise way, so what is the pattern? Because we can understand with 1 and 2, it's not a big problem, right? But what's with other numbers? So let's look at the general question. As you can see, the sum that we are working with, the general term of the sum is log 2 base log 2 argument a. Log 2 argument a, where a is some natural number. So we are looking at the number log 2a. Okay, so, and in many cases that we solved now, everything was related to the power of 2. Just remember, for example, when we had this power of 2 here 1, we had 1 1. When we had the power of 2 here, log 2 4, 4 was 2 to the power of 2, we had 2 here. When we came to the point of 8, it was 2 to the power of 3. And we had several 3 3 3 here. So, and how to understand what this number in general is, log 2a. In every case, when you consider this number, you should always consider that a is always in some interval between different powers of 2. For example, from 2 to the power of k to 2 to the power of k plus 1. Well, it's very easy to understand. If you look at numerical line, for example, let's look at numerical line, and you can divide it by with the intervals from powers of 2. For example, 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, then you go with 8, it's 2 to the power of 3, then you go with 16, it's 2 to the power of 4, and so on. And you can consider these intervals. For example, this one is included, this one is not included, this one is included, this one is not included, so the intervals do not intersect. And if you take any natural number, for example, it's from here. Obviously, this natural number is in some interval from 2 to the power of k to 2 to the power of k plus 1, right? So the power just changes only like plus 1. And obviously, it belongs to this interval. And it's very easy to understand that in this case, if it's true, then this log 2a is precisely equals k. So it precisely equals the power of 2 that is on the left end of this interval. And let's prove it. There is nothing difficult. So we know that a belongs to this interval. It is greater or equal to 2 to the power of k, but it's less than 2 to the power of k plus 1. And we are interested at log 2a. Well, let's take log 2 from each part of this inequality. And why we do it? Because if you take log 2 from this one, it becomes a great number, integer. It's simply k, less or equal than log 2a, and less than log 2 2k plus 1, it simply equals to k plus 1. And here you have numbers that are only different by 1. So it means that log 2a, it is less than k plus 1, but greater than equal to k. It means that we already found the interval of length 1 that contains this number. It means that log 2a belongs to the interval from k to k plus 1. And now the very simple question for you. If you have a number from this interval, what is the floor of this number? The floor of this number is the left end of this interval. It's k. So, and it means this is k. So, for any integer number that we can take here, and basically for any number from this interval, but we consider only integers because it's like a part of our sum. So this log 2 argument a is simply this power of 2 that is on the left side of our interval. Well, let's understand now clearly how our sum is organized. Well, we have a sum here, log 2, 1, log 2, 2, and so on. Let's understand in a normal way why do we have this pattern here, 3, 3, 3, 3. How many 3 do we have here and how many 4 do we have here? Because for us it's a very crucial question. Well, at first, why do we have this pattern with 3? And when it starts, we already told that this pattern of 3 starts when we go to the number 8. So, because when we go to the number 8, we go 8 is 2 to the power of 3. 8 is 2 to the power of 3. The next one will be 16. It's 2 to the power of 4. And if for any integer number a from here, log 2a equals 3. And how many do we have numbers here that will give us 3? Well, first will be here, and the next one will be on the step 1, on the step 1, on the step 1, and the next one will be just 1 behind 16. So if you consider how many numbers do you have here, you will get exactly 8 numbers. So it will be the first one and 7 here. So let's make it in a more general form, because we can't work like this with every interval. So and in the general form, it will look super simple. It will be even simpler than here, because we already know that if we consider interval from 2 to the power of k to 2 to the power of k plus 1, for any integer number a that we have here just from this sum, this value log 2a, floor of it, equals k. So how many integer a values do we have here? Well, our sum works like this. We always jump by 1 to the right side. We go 1, 2, 3, 4. So we jump through this natural number. So at first we come here, and it is the first one that will give us k. Then we go one step on the right, one step on the right, and one step on the right, and so on. And eventually the last number that will give us k is 1 behind the right end of this interval. So my main question for you, how many green integer points do we have in this interval? 1 here, 1 here, 1 here, 1 here. All these points represent natural numbers. How many natural numbers do we have on interval from 2 to the power of k included to 2 to the power of k plus 1 not included? And the question is super simple. If you consider any interval a, b, these are like integer numbers, a is included, b is not included, how many integer numbers do you have in this interval? The answer is always b minus a. It's very easy to show, just like a separate problem, because these are integer ends, and this one is included, this one is counted, and this one is not included. So this one is not a part of the interval. And you also consider all the points between them, and the number of integer points will be exactly b minus a. So in our case, the number of points here will be exactly 2k plus 1 minus 2 to the power of k, and because we have amazing properties of powers of 2, 2 to the power of k can be taken like this, and we will have here 2 minus 1, and it will be simply 2 to the power of k. So let's summarize what we have here. When we go through such interval, each number, integer that comes here will provide us the summand that is equal to k. It is power of 2 on the left end of the segment. And how many summands do we have here? How many summands do we have like this? Well, it's exactly the number of integers and integer values of a in this interval. And we know that the amount of integer numbers here is 2 to the power of k. 2 to the power of k summands. Each summand is k. What is the total sum of these values that belong to this interval? It will be obviously k to the 2 to the power of k. And this is it. And here it also explains why actually we had 8 numbers here. We already figured out that the amount of numbers here is 2 to the power of k. So 2 to the power of k here was 8, and here we have 8 numbers. Here from 16 to 32 we'll have 16 numbers. Each of these numbers will give us the amount of k, each summand. So you understand the structure. The structure is very simple, and it precisely explains us what pattern do we have here. The pattern looks like this. Each interval from 2 to the power of k to 2 to the power of k plus 1, if a go through this interval, the contribution to this sum, will be k to the times 2 to the power of 2k. So let's write the sum finally, and we will make like final writing, and after that the problem will be solved. So we will have 0, it's the first term. Let me remind you why. Because here we have 0, then we have 1, 1. So then we have 1, 1, plus 2 plus 2 plus 2. So in order for you to make everything simple, look, each summand here is 2. So k equals 2 on this interval. How many summands do we have on the next interval? It will be 2 to the power of 2. So we should have 4 numbers of 2, 2 to the power of 2. Let me write it like this, 2 to the power of 2, plus 3. The next summand is 3. If k is 3, we have it like on the next one. How many numbers do we have that will give us 3? Well, we already answered 2 to the power of 3. So it will be 8 numbers that will provide us 3. And 8 is actually 2 to the power of 3. Then we will have 4 plus 4 plus and so on plus 4, and the amount of these numbers will be 2 to the power of 4, which is 16, plus and so on, plus and eventually we can write that on the next interval the general form of this one will be k to the times to the 2 to the power of k. This is it. So it is a very simple structure of our sum. So let's write it once again. Here in a very short, in a very concise form, it will be 0 plus 2 plus k times 2 to the power of k. K is 2. 2 to the power of k is 2 times to the power of 2, plus k now is 3, and 2 to the power of k is 2 to the power of 3, plus k now is 4 times 2 to the power of 4, plus and so on, plus k times 2 to the power of k, and plus some other numbers. We have no, so I will explain what do I mean here, and it should be 19094, as I understand. So this sum is 9094. And what other numbers can be here? Well, this contribution comes when we already completely covered the interval with one end 2 to the power of k and the other end 2 to the power of k plus 1. So this interval is completely covered. So now here we may end up on the interval from 2 to the power of k plus 1 to 2 to the power of k plus 2, and there is no guarantee that we completely covered this interval, so we may be somewhere here, and each number a from this interval, what contribution will it give us to the sum? So what would be log 2 of a, the floor of this number? Obviously it will be again this power of 2 on the left side, so it will be k plus 1, k plus 1, k plus 1. So this at this point we can a little bit extend this sum here. It will be plus k plus 1. So I promise you that it will be very simple soon, so it's not that complicated as it may look now. K plus 1 just several times, and we should end up with 9094. Of course, we will not solve the problem in this way because it will be way too complicated. Just to try to make to find the sum in a general way, we'll make sort of assessment, because you understand that this 2 to the power of k, it increases very rapidly when k is a large number. For example, if k equals 10, 2 to the power of 10 is 1024, and this one 10 times 1024, it's already 10,000, and this sum on the left is already way larger than 1994. So it's even k equals 10 is not admissible for us. It's just way too large, and so we should just guess the value of a, the value of k that probably will work for us. So for example, let's start with k equals 5. In this case, it will be 5 times 2 to the power of 5 times 32. Well, it's probably not enough. We need something to be maybe pretty close to this one. It's about 150. Well, let's k be equal to maybe 6. If k is equal to 6, it will be 6 times 2 to the power of 6. It will be 64. Well, it's still like not a big number. We need something that close to 1994. So I'm just guessing what would be the last number here, and after that we will make an assessment, because the previous numbers are well known for us. So what other numbers work? For example, let's try maybe 8. So it will be 8 times 2 to the power of 8. 2 to the power of 8 is 16 times 16, which is 16, because 16 is 2 to the power of 4, right? So it will be 16, which will be 256 times 8, and it already looks promising. So let's look at the case when k equals 8. Will we have something that is close to 1994? Because this number will be pretty large. It will be already 2000, so it will be too much. Probably will we consider now k equals 7. Let's go with this one. So when k equals 7, then k to the power of 2k equals 7 times 2 to the power of 7. Well, what is 2 to the power of 7? It will be 2 to the power of 3, which is 8, times 2 to the power of 4, which is 16, and all of that times 7. So what is this value? It will be 8 times 16. It will be 80 plus 6 times 8, 48. It will be 128 times 7. It will be 700, 840. 840 plus 7 times 8, 56. It will be 896, like this one. And we obviously need to calculate the remaining numbers here. So let's do it, because in AIME we can't use calculator. So the numbers on the front will be like this: 0 plus 2 plus this one is 8, plus this one is 24, plus this one is 4 times 2 to the power of 4. 4 times 16, it's 64, right? 4 times 16, it's 64. Okay, 5 times 2 to the power of 5. The next one, 5 times 2 to the power of 5, it's 32. And 32 times 5, it's 160, plus 160. The next one will be 6 times 2 to the power of 6. 2 to the power of 6 is already 64, and the 64 times 6, it will be 360 plus 24 plus 384 plus, and so 7 times 2 to the power of 7. We already calculated it will be 896, and plus some sort of remainder will be here, plus some remaining part, and it should be equal to 1994, as we understand. Okay, so it is the last part that we have here is simple algebra, but we need to finish it, unfortunately, because it is the part of the problem, and we need to do it without calculator. So what we need to do here, we need to add up all these numbers to understand what the sum is equal to. We will do it in a reasonable way. So, for example, when we add them, let's just do it in appropriate manner. So 2, and the last one, the next one, let me check that it is 8. Yeah. So we will add this one, this sum will be equal to 34, right? 34. 34 plus 64 is 98. 98. This like difficult algebra, unfortunately, it is a part of AIME. So in some math competitions, it's not the case, but here you will have to do it if you want to successfully complete the problem. So 160 plus 98 is 258. 258, right? So let me just double check. Yeah, 258 plus this. So when I add these numbers, I want to add at first 4 to this one. It will be 900. So 900 plus 380, it will be 1280. 1280 plus 258. 1280 plus 258, and it will be 83151. 1538. So it is the sum that we got here. So 1538 plus sum of several elements, and it should be equal to 1994. Let's remember what we are finished here. So the last number here was 7 times 2 to the power of 7. So here it was the last one, and it was the contribution from the interval with the left end 2 to the power of 7 and the right end 2 to the power of 8. And here we will have a contribution already when we go when our integer numbers go from the interval 2 to the power of 8 to 2 to the power of 9. So we're already in this interval, and each contribution of each number here will be simply 8, will be this power. So plus 8, plus 8, plus 8, and so on, plus 8. So in here we can make an equation. 1538 plus 8 times k equals 1994. And let's solve this equation. We'll understand how many numbers 8 do we have here. So 8k equals 1994 minus 1538. 1994 minus 1538. So let's calculate. 14 minus 8 is 6. Here we have 8 minus 3 is 5. Here we have 4. 456. 456. And if we divide 456 by 8, what will we get? So k equals 456 divided by 8. So it will be 400 by 8 plus 56 by 8. So this one is simply 50, and this one 7. Yeah, it will be 7. So 7 times 8 is 56, so 57. Okay, so here we should have, in order this equality to be true, here we should have exactly 57 eighths. So 57 times 8. So 1 8 we go when we get here, when we're exactly at 2 to the power of 8. When a is equal to 2 to the power of 8, it is the first a that we have. When a is equal 2 to the power of 8 plus 1, it is exactly the second 8 that we have here from a contribution from this one. When a is equal 2 to the power of 8 plus 2, we will have the third contribution, the third 8 here. And we have 57 times. Okay, so here, when we have this 8, we can tell that in this case, a is equals 2 to the power of a. And here, a equals 2 to the power of a plus 1 plus 2, and so on. And as you can see here, the last one obviously will be a equals 2 to the power of 8 plus 56. If you look, 57 numbers, it is the first number, and here you will have exactly 57 numbers. So the last contribution should be from this number, and it is the final number in our sum. In this case, everything will perfectly add up, and it is the final value of n that should be here. So let's calculate this number. 2 to the power of 8 plus 56. 2 to the power of 8 plus 56. Let's remember, what is 2 to the power of 8? So it will be 2 to the power of 4 times 2 to the power of 4. So 16 times 16, 256 plus 56. It will be 256 plus 56. It will be 312. And 312 is the right answer. It means that this sum precisely equals to 1994 when n is 312, and it is the right answer for this problem. Okay, we have the last problem for today, number 5, and again it is related to sums, and let me quickly explain what the problem is about. So for every positive integer n, for any natural number, p of n is the product of its non-zero digits. What does it mean? Well, for example, if we have a number like 1, 2, 3, then the product of its digits is 1 times 2 times 3, simply 6. But if we have a number like 101, then when we calculate the product of its digits, we should only calculate non-zero digits, so only non-zero digits should be included, and in this case it's equal to 1 times 1. If we have a number like 540, then the product of its non-zero digits, p of n, is 20. So as simple as that. And after that we construct the sum like this: p of 1, p of 2, p of 3, and p of 999. What does it mean? That for any natural number from 1 up to 999, we calculate the product of its non-zero digits. It is assumed that for the first numbers, like from 1 to 9, that have only one digit, obviously the product is simply these digits. For example, p of 2 equals 2, p of 3 equals 3. That's what's written here. So this number consists of 999 summands. Well, and obviously when you add all of them up, you will have a pretty large number at the end, number s. And you are asked what is the largest prime factor of s. And initially it looks pretty complicated because you have a lot of summands, you have a large sum, and how to solve this problem. Once again, in every case when you deal with sums, you should always understand what is the structure of the sum, how is it organized, is there some pattern, and the best scenario for us is to start from the first numbers and to understand what would be the first summands here. For example, for 1, on the right side we will write p of 1 is 1, the product of non-zero digits. For 2, the product of non-zero digits is 2. For 3, it's 3. For 4, it's 4, and so on. And for 9, the product of non-zero digits is of course 9. Let's go to the next 10 numbers. 10, 11, 12, and so on, 19. So as you can see here we have exactly 10 numbers, because 9 numbers here and 1 number here, but here we have exactly 9 numbers. So there is a little bit different situation, because here we don't have 0. Well, for these numbers, the product of non-zero digits for 10 is simply 1, the product of non-zero digits here is 1, the product of non-zero digits is 2, for 13 it will be 3, and for 19 it will be 9. So as you can see here, for example, for these numbers and for these numbers, everything looks the same. The only thing that we have 1 in addition here. Let's continue and let's understand if there is some pattern here. For 20, the product of non-zero digits, p of 20, is simply 2. For 21, it's also 2. For 22, it's 2 times 2. For 23, it's 2 times 3, and so on. And for 29, it's 2 times 9. And you immediately can see that for this column and for this column, the situation is very, very similar. This column is simply this one multiplied by 2. Because we have here 2 on the first place, it contributes to the product of non-zero digits, and it provides additional factor of 2 everywhere. So, and we have a pattern that looks like this. We can take these numbers, and these numbers, all of them here we have multiplied by 2. And it's very easy to understand that when we move to 30, it will be exactly the same story. So 30, the product of non-zero digits is 3, and we can tell it like 3 times 1. No, it doesn't matter. We'll do it like this. 32 is 3 times 2. 33 is 3 times 3, and so on, and 39 is 3 times 9. And again, you can see that this column is exactly the first column multiplied by 9. So initially it looked like there is a pattern here, but it looks more like a strong, more useful thing to look at the pattern here, because every next column will be directly related to the first one. It will be simply multiplied by some number. And of course, if we look at the last two-digit numbers like 90, 91, 92, and so on, 99, you will have here 9, here you will have 9, here you will have 9 times 2 for 92, for 93 you will have 9 times 3, and for 99 you will have 9 times 9. And again, it is the first column just multiplied by 9. Okay, so now we have a very simple pattern here. We are ready to calculate the next sum that looks like p of 1 plus and so on plus p of 9. It is the sum of these digits, and so on up to p of 99. P of 99. So this sum consists of 99 different numbers, and we simply can add up all these columns. And you can see the strongest pattern, the most useful for us. We noticed here that this column here it's multiplied by 2, here by 3, here by 9. And we will start from this one. So we will separate this sum of numbers from 1 to 9. What this sum is equal to? Well, if you know the basics of arithmetic sequences, you can calculate this one, and it will be 45, right? 1 plus 9, first plus the last one, first one plus the last one, times how many numbers you have, divided by 2. This sum is 45. So this is 45. The next one will be one larger, so it will be 46. Plus 46. Here you can factor out 2 when you add all this number. You factor out 2, and inside the parentheses you will have exactly this sum. So this sum of this column will be 2 times 46. The sum of this column will be 3 times 46. And eventually the sum of the last column will be 9 times 46. Well, good enough. So here, of course, what we want to do, we want to factor out 46 everywhere, because you can see 46 is present in every summand, and it makes a lot of sense to factor it out. And what will we have? Inside the parentheses, we'll have 1 plus 2 plus 3 and so on plus 46. I'm sorry, 1 plus 9. Of course, plus 9 here. And 46 is factored out, and here we have 45 plus this sum. This one is exactly 45, and the total sum equals 45 plus 46 times 45. Of course, when you have this sum, it makes a lot of sense to factor out 45, and inside the parentheses we'll have 1 plus 46. It will be 47. So the total sum equals 45 times 47. And it is our first result. It is the sum of first 99 summands. Okay, at the moment it looks very simple, and it really will not be more difficult. So let's look at the next numbers. It makes a lot of sense to start from 100, then we go to 101, 102, and so on, and the last one 110. So I'm sorry, yeah, 109. It will be the last one. So here we have 10 numbers again, and you have a very similar situation with this one. When you started from 10 to 19, the product of non-zero digits here is 1, here is 1, here is 2, here is 3, and here is 9. Again, the total sum is 46, but when you move to the next 10 numbers, 110, 111, 112, 112, 113, and so on, 119, here you will have a very similar pattern. The product of non-zero digits is 1, 1, 2, 3, and 9. So in the first two columns, in this one and this one, everything is completely the same. But of course, when we go to the next column, the situation will be different, because here we will have a contribution of 2. This one, 1, 2, the first one will be 0, 1, 2, 1, 1, 2, 2, and eventually 1, 2, 9. So the product of non-zero digits here is 2, here is 2, and here is 2 times 2. Just let's not multiply that as 4, because 2 times 2 is just better for us. And here it's 2 times 9. And again, you can see that this column is exactly this column multiplied by 2. And of course, you can understand that we can continue, and eventually when we go to 190, the last 10 numbers, 190, 191, 192, 193, and so on 199, what would be this column? The product of non-zero digits here is 9, here is 9, here is 9 times 2, here is 9 times 3, and here is 9 times 9. And as you can see, this column is precisely this one multiplied by 9. So, and if you add up all these numbers, what sum will you have here? The sum will be exactly p of 100, which is this number, plus p of 101, which is this number, and so on, and you will finish at p of 199. So here we have exactly 100 numbers. The sum of these is 46. It's the sum of the first column. The sum of the second column is also 46. The sum of the third column, you can factor out 2 here, and it will be 2 times 46 plus, and so on. The sum of the last column, you can factor out 9, and the sum will be 9 times 46. Well, looks very simple at the moment. And here, with this sum, you can factor out 46, and the total sum in parentheses will be 1 plus 2 and so on plus 9 again, and 46 in the front. So it will be 46 plus 46 times, this one is 45. It will be 46 plus 46 times 45. And again, we can factor out 46 here. In parentheses, we will have 1 plus 45, and it will be simply 46. So the sum is 46 squared, which is an amazing result. So the sum of these numbers is simply 46 squared. And if you make like a reasonable approach, you can understand what will happen in the next 100 numbers. If you do the numbers, for example, you start from 200, 201, and so on, 209, then you go to 210, 211, and so on, 219. You can see that in this column, everything will be like here, but multiplied by 2. It will be contribution because of 2 on the first place. Here you will have exactly like this, but once again, everything will be multiplied by 2 because of this contribution, 2 on the first place. And this pattern will repeat in every next column, in the third, in the fourth, in the ninth column here. Every number will be twice larger than number in the ninth column here, because you have a contribution from 2 on the first place. So, and if you add up all these numbers for 200, so basically, if you add numbers like p of 200 plus p of 201 plus on plus p of 299, what can you tell about this sum? Well, this sum is exactly 2 times larger than this sum, exactly twice as this sum, because p of 200 is twice larger than p of 100, p of 201 is twice larger than this one, and the last one is twice larger than this one. And it means that this sum is simply 2 times 46 squared. 2 times 46 squared. Very simple result. And of course, for other sums, like for the sum, for example, p of 300 plus and so on plus p of 399, it will be 3 times larger than this sum because of the contribution of 3. And this sum will be equal 3 times 46 squared. And eventually, the last sum, p of 900 plus p of 999 will be exactly 9 times larger than this sum because of contribution of 9 on the first place. So it will be 9 times 46 squared. Let's sum up what we have. We calculated every sum from here. We just separated it into several sections. The first section was this sum, and it was simply 45 times 47. The second section was sum from p of 100, p of 199, and this sum is simply 46 squared. Then sum of the next 100 numbers is twice of this one. The sum of the next 100 numbers is 3 times this one, and the sum of the last 100 numbers is 9 times this sum. And let's make the total estimation. So the total sum that we are looking for, the sum of numbers like p of 1 and so on, p of 199. So we will write numbers already. So it will be 45 times 47, it's our first one, 45 times 47, plus the next one will be 46 squared. So 46 squared plus 2 times 46 squared plus and so on plus 9 times 46 squared. Well, what can you tell about this sum here? This sum you can factor out 46 squared, and how will it look? It will look like this. 46 squared is factored out, and the sum in parentheses will be 1 plus 2 and so on plus 9, which is 45. And this total sum equals 45 times 47 plus 46 squared times 45. And immediately what you want to do here, you want to factor out 45. So it will be 45 times 46 squared plus 47. Okay, we found this number S. It is exactly the sum of these 999 numbers. As you can see, initially it looked very complicated, but because we made like a reasonable approach, we were able to see very simple pattern how numbers are organized here. And after that, we can say that this number S looks like this. So let's write our result here. So S equals 45 times, so 46 squared plus 47. So 46 squared plus 47. So, and what they ask us to do, they ask us to find the largest prime factor of S. Okay, so S is already factorized, which is a great news. So we already know that S is divisible by 45 and it's divisible by this large number. We are looking at the largest prime factor of S. We are looking at the largest prime number that divides S. Well, it doesn't make any sense to look this prime number inside 45 because the only prime divisors here is 3 and 5. Well, 3 squared times 5, and from 45 S has only prime divisors like 3 and 5, which is very small number. So of course, if we look at prime factors and we want the largest prime factors, we should look at this one. 46 squared plus 47. Let's calculate this one. 46 squared. So it will be 46 times 46, 6, 3, 27, 4, 2 and 18. So this product is 6, 1, 1, and it should be 2. 2, 1, 1, 6. Okay, 2, 1, 1, 6 plus 47. 2, 1, 1, 6 plus 47. It should be 3, 1. It will be 6, 2, 1, 6, 3. So it will be 45 times 2, 1, 6, 3. Well, this number is pretty large, and initially it looks very difficult to find this the largest prime factor of this number. However, if you know the rule when number is divisible by 3, here you have a great hint. The sum of its digits is obviously divisible by 3. It means that this number is divisible by 3, and you should obviously divide it. And if it's very easy to divide by 3, you can do it even just immediately. It will be 45 times 3 times 721. 3 times 721 is this number. Okay, so if we are looking at the largest prime factor, this one gives only 3 as a prime factor, this one gives 3 and 5. Obviously, we need to look at 721. And again, what do we have here? It's not unfortunately divisible by 3, but it's very, very easy to notice that it's divisible by 7. And again, you can do it pretty fast. Let's divide it by 7. What will we have? We will have 45 times 3 times 7 times 103. It is your factorization. 7 is a prime divisor of S. Well, again, it's a very small number, but 103 looks very promising. If it's a prime number, it would be the largest prime divisor of S. Let's check if 103 is a prime number. If you want to check that some number n is a prime, you should only check its divisors up to the square root of n, and this is it. In this case, the square root of this number is something about 10. And in addition, you can understand that you shouldn't check all the numbers from 1 to 10. You should only check the prime numbers from 1 to 10. If none of the prime numbers that is less than square root of n divides your number n, then it will be a prime. It's just a very simple thing. So in our case, we should only check numbers from 1 to 10 and only prime numbers if they divide 103. So we have 2 doesn't work. 3 doesn't divide 103 because the sum of its digits is 4, not divisible by 3. 4 we don't need to check because it's a composite, not a prime. 5 is a prime number, obviously not divisible by 5. 6, 7. 7 is an interesting one. It is obviously not divisible by 7. Well, you can check because 98 it's divisible by 7 and it's the closest one. 98 that is divisible by 7 that is close because 98 is 70 plus 28 and this is it, yeah. So and it's not, it doesn't work. 8, 9 and 10, this is it. So 103 is a prime number and 103 is the largest prime factor of S, and the problem is solved.